Welcome back. Today I wanted to take a look at a central limit theorem problem. The weights of pennies, in other words, this problem is going to require us to know a little bit about the central limit theorem. I'll read it first. The weights of pennies minted after 1982 are approximately normally distributed with a certain mean, 2.46 grams, and a certain standard deviation, 0.02 grams. What's the probability that in a simple random sample of 10 pennies, minted after 1982, that we would obtain a sample mean of at least 2.465 grams? Well, this is a central limit theorem problem. And how do we know? Well, let's recite the central limit theorem for starters. What does it say about the distribution of all possible sample means of a fixed sample size? So your trigger is you've got a sample size of 10, and you're trying to find the probability that we would obtain a sample mean of at least 2.465 grams. Now, with repeated experimentation. So we know what the central limit theorem says about this. So I'll just help you jog your memory about the central limit theorem. It says, despite the shape of the population, the distribution of sample means of a fixed sample size will always be approximately normal, with a mean of the sampling distribution equaling to that of the population mean, and the standard deviation of the sampling distribution equal to sigma over root n. And this approximation gets better as n gets larger and larger and larger. So here we have a small sample size. Let's take a look. So the first thing I see is that they're asking us, for the probability. And we know that's going to involve a z-score. So in this chapter, regarding the central limit theorem, your z-score is going to be x bar minus mu over sigma over root n. Now remember, this quantity in the denominator here, this sigma over root n, is called the standard error of the sampling distribution of sample means, which I know is a mouthful, a lot of language. That's called the standard error. Okay, so let's just think about what we know. Sample mean. Well, we're looking, what's the probability that we would obtain a sample mean of at least 2.465 grams. So you really just have to be careful what you're plugging where. So 2.465 minus this, if you want to note to self, is the population mean. I like to think of it as that which you observe. I like to think of it of observed minus population. This is what you've observed from your sample, right? So the population mean was 2.46 over sigma over root n, the standard error of the sampling distribution. So 0.02. We know that standard error is affected by sample size. We have a small sample size here, 10. Okay. Now what we have to do is crunch this out on our calculators. I'll hit pause and get a z-score. Okay, so by now you've probably crunched that out and got a z-score of 0.79. Okay, now we want to know the probability of obtaining a sample mean of at least 2.465 grams. So now let's think about how we're going to draw this on the standard normal curve. Okay, so here's the standard normal curve, which is centered at 0. And you say, why are we drawing the normal curve? Because the central limit theorem says that the distribution of all sample means of a fixed sample size will be normal, despite the population, will be approximately normal. With repeated trials, with enough repetition and a large enough sample size, it becomes very normal. But now we see we have a z-score here of 0.79, and now we know that the area to the right of this z-score is going to be that probability that we're looking for. Now, in my class, we use the calculator, and we hit normal CDF, 0.79, comma, and we use 99999 to represent infinity. Or you could look up 0.79 on a z-table. Let's take a look. So just to refresh your memory, if you're using one of these kinds of calculators, second distribution, normal CDF, enter, and then the z-score, which was 0.79, and then comma, infinity, because we're shading to the right, which is to infinity. We'll just represent that with a bunch of 9s, and hit enter. So we have about a 21% chance of that event happening. So let me go back to this problem then. So then again, what's the probability that a simple random sample of 10 pennies, minute after 1982, we obtain a sample mean of at least 2.465 grams? Notice that was a 21% chance of that happening. Now, big note to self, notice the sample size was small. You have a fairly high chance of that happening. What if the sample size was larger? So that's a good question. So what if you had, say, 50 pennies? Okay, so let's just play that game a second. 50 pennies. Well, we know the size of the standard error is affected by the sample mean. So let's just play with that a moment. If that were the case, then your z-score would have been 2.465 minus the 2.46 divided by 0.02 over root 50. So clearly you're going to get a different z-score and in turn a different probability. Well, let's take a look. You can type that in with me to get the z-score. So you get a z-score of 1.78 now. Well, you're living way further out on the curve, so the probability or the area to the right of 1.78 is less. So if we normal CDF, 1.78 to infinity, now we only have a 4% chance of that occurring. So in other words, makes sense. If your sample size is small, you're going to have a larger probability of, observing sort of a divergence or a difference from the population mean. But if your sample size is larger, say 50, the probability of observing such a divergence from the true population mean is going to be even less. So, big note to self, try playing with the sample size. Play with sample size to see how having a larger sample size affects the probability of you obtaining a certain sample mean that is different from the proposed population mean. Okay? Good luck.